What if you could witness the most astonishing transformation Earth has ever undergone? What wonders would we discover if we traveled hundreds of millions of years into the past, to a world where life was only beginning to slowly conquer the surface? Dear time traveler, today we embark on a journey through one of the most fascinating chapters in our planet's history, spanning from 600 million to 66 million years ago. An interval during which Earth evolved from a world inhabited solely by simple life forms in the oceans into a planet dominated by colossal creatures such as the dinosaurs. Imagine vast seas filled with strange, eyeless organisms, continents breaking apart and colliding in slow yet monumental tectonic dances, and atmospheres whose composition shifted alongside the emergence of new forms of life. It was a time of accelerated evolution, of mass extinctions, and of astonishing rebirths. Prepare to explore global ice ages, oceans teeming with trilobites, the first tentative steps of life onto solid ground, and the absolute dominance of giant reptiles. This is a journey through the ever-changing landscapes of a living Earth, dynamic and in constant metamorphosis. But before we begin this thrilling adventure into deep time, don't forget to leave a like and subscribe to the channel so we can continue exploring the secrets of the past together. Thank you, and let the journey begin. Imagine a primordial world around 635 million years ago, a time even before the famous Cambrian Explosion. This was the Ediacaran Period, the final chapter of the Neo-Proterozoic era and the true dawn of complex life. For eons, our planet had been dominated almost exclusively by microorganisms. But during the Ediacaran, everything began to change. It was then that the first large multicellular organisms appeared, strange and enigmatic forms, unlike most life we know today. They are collectively known as the Ediacaran biota. Most of these creatures were soft-bodied and displayed a wide range of unusual shapes: flat discs, immobile fronds resembling quilted plants, or structures that looked like padded, segmented blankets. They lived primarily on the shallow seafloor, absorbing nutrients directly from the surrounding water or from the sediments beneath them. Unlike modern animals, many lacked mouths, digestive systems, or obvious appendages. Their relationship to today's major groups of life remains one of the great mysteries of paleontology, as many of them appear to have no clear modern descendants. The Ediacaran was also a time of profound environmental transformation. At its beginning, Earth was emerging from a series of extreme global glaciations known as the Snowball Earth events, periods when much of the planet was likely covered in ice. As the ice gradually retreated, oxygen levels in both the oceans and the atmosphere began to rise. This increase was critical, as oxygen is essential for sustaining larger and more complex organisms. These changing conditions opened an unprecedented evolutionary window. This period was foundational because it represented nature's first large-scale experiment with multicellular life and cellular differentiation. Although many Ediacaran organisms disappeared by the end of the period, they laid the biological and environmental groundwork for the explosion of diversity that would follow in the Cambrian. It was a quiet but essential prelude to the complex life that inhabits our planet today. Emerging from the phase of biological experimentation that defined the Ediacaran, Earth stood on the brink of a transformation of astonishing magnitude. This was the threshold of the Cambrian, the first period of the early Paleozoic, spanning from roughly 541 to 485 million years ago. What followed was a burst of biological diversity so extraordinary that geologists and paleontologists have named it the Cambrian Explosion, an event that would lay the foundations for all future complex life. Geologically, the Cambrian was marked by a major reorganization of the continents. While the supercontinent Gondwana dominated the southern hemisphere, the northern hemisphere was fragmented into smaller land masses such as Laurentia, Baltica, and Siberia. This configuration created vast continental shelves flooded by shallow seas. These epicontinental seas, warm and well lit, provided the ideal environment for the proliferation of marine life. The abundance of carbonate sediments on these seafloors is the reason we possess such an exceptional fossil record from this time, especially in sites like the Burgess Shale in Canada or the Maotianshan shales in China. The global climate was predominantly warm and stable, with no major glaciations, maintained by high levels of atmospheric carbon dioxide that kept ocean waters relatively mild. The Cambrian explosion itself remains one of the greatest mysteries and marvels of evolutionary biology. In just a few million years, a fleeting moment in geological time, the fossil record reveals the sudden appearance of nearly all the major animal phyla that exist today. Before this, complex life was rare and largely soft-bodied. During the Cambrian, however, organisms developed skeletons, shells, and exoskeletons that fossilized far more readily. Several hypotheses converge to explain this dramatic burst of innovation. Rising oxygen levels in the oceans that supported more active metabolisms, the emergence of eyes and the resulting intensification of predator-prey interactions that fueled an evolutionary arms race, and the development of key regulatory genes known as Hox genes, which may have enabled the rapid emergence of new body plans. Together, this combination of factors transformed the oceans into a bustling crucible of biological innovation. Among the most iconic Cambrian creatures, trilobites are undoubtedly the most famous and abundant. These marine arthropods, with their segmented bodies and compound eyes, displayed an astonishing diversity of forms and sizes, ranging from just a few millimeters to more than half a meter in length. They occupied a wide range of ecological niches, acting as scavengers, filter feeders, or small predators. Alongside them thrived brachiopods, shell-bearing organisms that filtered food from the water, and archaeocyathids, the first large-scale reef builders, which created complex marine communities. Yet Cambrian oceans were also home to formidable predators. Anomalocaris, a giant arthropod for its time, could reach lengths of up to 1 meter. Equipped with large grasping appendages and a circular mouth lined with sharp plates, it was the apex predator of its ecosystem, capable of hunting trilobites and other armored creatures. The presence of such a sophisticated predator suggests that well-structured food webs were already firmly established. Other remarkable organisms, such as Opabinia, with its 5 eyes and flexible proboscis, and Hallucigenia, with its spiny back and bizarre proportions, testify to the experimental and often strange body forms life explored during this period of rapid diversification. Even the earliest chordates, the ancestors of all vertebrates including ourselves, made their appearance during the Cambrian. Fossils such as Picaia gracilens, a small worm-like organism possessing a notochord, a flexible supporting rod, reveal the humble beginnings of our own evolutionary lineage. Though inconspicuous during the Cambrian, these early chordates represented a crucial innovation that would, millions of years later, give rise to fishes, amphibians, reptiles, birds, and mammals. The end of the Cambrian wasn't marked by a single catastrophic mass extinction, but rather by a series of smaller extinction pulses, often linked to fluctuations in sea level. These events trimmed existing diversity and opened ecological niches for new groups to radiate in the periods that followed. In essence, the Cambrian was a crucible of evolution, a time of unprecedented biological experimentation. It was the moment when life dared to embrace complexity, mobility, predation, and defense, laying the groundwork for all major animal groups and transforming the oceans into dynamic, vibrant ecosystems. For the first time, Earth was becoming a truly biological planet in the fullest sense of the word. Following the Cambrian Explosion, life on Earth continued its evolutionary journey during the Ordovician, a period spanning from about 485 to 443 million years ago. It was a time of remarkable diversification of marine life and, crucially, of the very first and tentative steps of life onto land, laying the groundwork for the future colonization of the continents. Yet its conclusion would be marked by one of the most severe mass extinctions in the planet's history. From a geological perspective, the Ordovician was an era of continuous continental motion. The supercontinent Gondwana dominated the southern hemisphere, while smaller land masses such as Laurentia, the precursor of North America, Baltica, corresponding to much of modern northern Europe, and Avalonia, which today forms parts of Western Europe, continued to drift across the globe. Collisions between these plates triggered major orogenic events, meaning the formation of mountain ranges. One key example was the tectonic orogeny, which affected the eastern margin of Laurentia and resulted from the collision of island arcs with the continent. These tectonic processes not only reshaped the landscape, but also influenced ocean circulation and global climate patterns. Throughout most of the Ordovician, sea levels were exceptionally high, flooding vast areas of continental shelves. These extensive epicontinental seas, shallow and warm, provided ideal habitats for marine life, as evidenced by the widespread deposits of limestone and black shales from this period. The global climate during much of the Ordovician was predominantly warm and humid, continuing the temperate conditions established during the Cambrian. Atmospheric carbon dioxide levels were high, sustaining a strong greenhouse effect that kept ocean temperatures elevated and prevented the formation of significant polar ice caps. Toward the end of the period, however, Earth experienced a dramatic climatic shift. A trend toward global cooling culminated in a massive glaciation, a late but decisive change that would have devastating consequences for life. In Ordovician oceans, marine life reached unprecedented levels of diversity and ecological complexity. Ecosystems were maturing, with increasingly intricate food webs. Brachiopods underwent an extraordinary adaptive radiation, becoming one of the most abundant groups on the seafloor. Alongside them, bryozoans and crinoids, often called sea lilies, flourished, forming vast underwater meadows and contributing to the growth of reef-like structures. Graptolites, colonial organisms that floated or drifted in the water column, diversified enormously, and today serve as excellent index fossils for dating Ordovician rocks. Perhaps the true stars of Ordovician seas, however, were the nautiloid cephalopods. These mollusks, distant relatives of modern octopuses and squids, reached their peak in size and diversity during this period. Armed with straight or gently curved conical shells, some forms, such as the iconic Endoceras, could grow to astonishing lengths of up to 6 meters. They were formidable predators, dominating marine ecosystems as true apex hunters. Another crucial and fascinating evolutionary development was the continued diversification of the earliest vertebrates, jawless fishes known as ostracoderms. These primitive fishes, which had already appeared during the Cambrian, were protected by bony armor plates. They were primarily filter feeders and represent the ancestral stock from which all later vertebrates would evolve. Here lies one of the most remarkable contrasts of the Ordovician world. While the oceans teemed with life, the land surface remained largely barren and inhospitable to complex organisms. yet the earliest signs of terrestrial colonization were beginning to emerge. Fossil evidence reveals the presence of spores from primitive land plants. This suggests that simple plant life, likely resembling modern mosses or liverworts, had begun to venture onto the margins of aquatic environments. These early plants lacked complex vascular systems and true roots, and were confined to very moist habitats. Still, this represented the first hesitant yet monumental step toward the transformation of Earth's continents. The story of life in the Ordovician culminated in a catastrophic event: the Ordovician Silurian mass extinction. This was the second largest mass extinction in Earth's history. Occurring in two main phases around 443 million years ago, it was closely linked to a dramatic global climate shift. The first phase was triggered by extensive glaciation. As Gondwana drifted towards the South Pole, massive continental ice sheets formed, locking away enormous volumes of water. The result was a rapid and global drop in sea level, estimated at up to 100 meters or more. This retreat of epicontinental seas devastated marine life by destroying or drastically altering vast shallow water habitats. The second phase of the extinction followed the peak of glaciation and is thought to have been associated with warming and the melting of ice sheets. This led to a rapid rise in sea level, but also likely caused changes in ocean chemistry, including periods of anoxia, or oxygen depletion, in deeper waters. The combined effects produced a biological catastrophe. It is estimated that the Ordovician Silurian extinction eliminated around 85% of marine species, severely impacting groups such as trilobites, brachiopods, and graptolites. It was a devastating blow to life on Earth. Yet, as so often in deep time, the loss of dominant species left ecological niches vacant, setting the stage for recovery and the radiation of new forms of life in the following period, the Silurian. After the devastating Ordovician Silurian mass extinction, life on Earth faced a new dawn. The Silurian, spanning from about 443 to 419 million years ago, was a period of remarkable recovery and, most importantly, the threshold of terrestrial life. This is the chapter in which Earth begins to take on a green hue, and the first living organisms take their tentative steps beyond the aquatic realm. Geologically, the Silurian was a time of relative tectonic calm compared to earlier eras, yet the movement of continental plates continued to reshape the planet's geography. The supercontinent Gondwana remained dominant in the southern hemisphere, but its position and extent allowed climatic conditions to stabilize. In the northern hemisphere, however, the smaller continents of Laurentia, Baltica, and Avalonia began a process of convergence and collision. This gradual union would culminate in the formation of a new supercontinent known as Euramerica, or Laurussia, in the following period. Tectonic collisions during the Silurian gave rise to major mountain-building events, such as the Caledonian orogeny, which uplifted impressive mountain ranges whose geological scars can still be seen today in regions like Scotland, Norway, and the northern Appalachians of North America. These newly formed mountains altered wind patterns and precipitation, influencing regional climates. Sea levels during the Silurian were generally high and relatively stable. The melting of Ordovician glaciers contributed to a global rise in sea level, once again flooding vast areas of continental platforms. These shallow, warm epicontinental seas provided ideal conditions for the expansion of marine biodiversity and the growth of extensive reef systems. Silurian marine sediments, rich in limestones and shales, stand as clear evidence of these productive environments. The global climate throughout the Silurian was predominantly warm and stable, with few major fluctuations. Temperatures were mild, and the absence of large-scale glaciations allowed marine ecosystems to recover and flourish. Atmospheric carbon dioxide levels, though somewhat lower than during the Ordovician, remained high enough to sustain a greenhouse climate. This climatic stability was a crucial factor that enabled the diversification of life, both in the oceans and on land. In Silurian seas, marine life experienced a strong recovery and diversification following the Ordovician extinction. Marine ecosystems became increasingly complex and specialized. Coral reefs underwent a spectacular resurgence, expanding widely and forming massive structures. Unlike modern reefs dominated by stony corals, Silurian reefs were built primarily by tabulate and rugose corals, together with stromatoporoids, a group of sponge-like organisms that secreted calcareous skeletons. These reefs were not only impressive in size, but also functioned as true underwater cities, providing countless ecological niches, shelter, and food for a wide variety of invertebrates. Brachiopods and bryozoans remained abundant, rapidly regaining their diversity. Crinoids, or sea lilies, continued to thrive, forming extensive underwater meadows with their flexible stalks and filtering arms. Yet the most iconic and feared inhabitants of Silurian seas were the eurypterids, commonly known as sea scorpions. These marine arthropods, some of which reached colossal sizes of up to 2 meters in length, such as Jacalopterus rhenaniae, were apex predators in shallow and brackish marine environments. With their large claws and segmented bodies, they were the aquatic counterparts of today's large terrestrial predators, using their swimming limbs for agile movement and their chelicerae to crush prey. The presence of these giants points to a robust and complex marine food web. Perhaps the most transformative evolutionary development in Silurian oceans was the dramatic diversification of fishes. Jawless, armored fishes known as ostracoderms continued to thrive. However, the Silurian is especially notable as the period when the first jawed fishes appeared and began to diversify. The evolution of jaws was a monumental turning point in vertebrate history, opening entirely new dietary possibilities and predatory strategies. Among these early jawed pioneers were the acanthodians, small fishes with bony spines that gave them a partially armored appearance, and the placoderms, which, although they had not yet reached their peak size and diversity, already displayed the characteristic bony armor on the head and thorax. The emergence of jaws allowed fishes to bite, chew, and capture larger and tougher prey, fundamentally reshaping the dynamics of aquatic ecosystems. And now we arrive at the most revolutionary milestone of the Silurian, the colonization of land by complex life. Until this point, the continents had been barren, rocky deserts, exposed to wind and intense ultraviolet radiation, with life confined almost entirely to the oceans. During the Silurian, however, the first primitive land plants made their bold appearance. These pioneering plants, likely evolving from green algae, were small and simple, lacking true roots, stems, and leaves as we know them today. Cooksonia, one of the oldest known vascular plants, is a key example. These plants were only a few centimeters tall and lived in very moist environments, close to the shores of lakes and rivers, or in intertidal zones. How did these plants manage to conquer such a hostile environment? They evolved crucial adaptations: a waxy cuticle to prevent dehydration, stomata, small pores that regulate gas exchange, and, most importantly, a primitive vascular system, specialized tissues for transporting water and nutrients throughout their small bodies. This innovation was essential for survival outside an aquatic environment. Their reproduction relied on spores dispersed by the wind, allowing them to spread into new areas. the appearance of these plants was a true game changer. By establishing themselves on land, they began to transform the planet's surface, releasing oxygen into the atmosphere and, just as importantly, initiating the formation of the first soils through the weathering of rock and the accumulation of organic matter. This soil-forming process was fundamental for the future colonization of land by more complex life forms. Following the spread of plants, or perhaps coexisting with them along moist margins, the first terrestrial arthropods made their appearance. Fossils of early millipedes and primitive scorpions date back to the Silurian. These pioneers ventured onto land, likely in search of food such as plants, detritus, or other small invertebrates. Scorpions, for example, already possessed many of the defining features of their modern descendants, including pincers and a stinger-tipped tail, indicating their role as predators even in the earliest stages of terrestrial life. Adapting to air breathing and preventing water loss were among the greatest challenges these invertebrates had to overcome. The Silurian, therefore, was a period of immense significance. It was not only a time of recovery and flourishing marine life, marked by the resurgence of reefs and the rise of jawed fishes, but also the era in which life made a bold leap from water onto land. These first hesitant steps laid the foundations for the widespread colonization of the continents, setting the stage for the explosion of terrestrial life that would define the periods to come. The world would never be the same again. Earth was beginning to turn green. Following the recovery from the Ordovician Silurian extinction and the earliest steps of life onto land, Earth entered the Devonian, a period spanning from about 419 to 359 million years ago. Often known as the Age of Fishes, it witnessed an extraordinary diversification of aquatic life and, even more transformative, the establishment of the first true forest ecosystems on land. For the first time, Earth began to resemble the green landscapes we recognize today. Geologically, the Devonian was shaped by major continental collisions. The land masses of Laurentia, Baltica, and Avalonia merged to form the supercontinent Euramerica, also known as Laurussia. These collisions triggered significant mountain-building events, including the Akkadian orogeny and the continued uplift associated with the Caledonian orogeny, raising vast mountain ranges across what are now parts of North America and Europe. Sea levels remained relatively high throughout much of the period, creating extensive shallow epicontinental seas that were ideal for marine life. The global climate was predominantly warm and stable, supported by an atmosphere rich in carbon dioxide. However, as terrestrial plants expanded across the continents, they began to draw down atmospheric carbon, contributing to a gradual cooling trend towards the end of the period. In Devonian oceans, aquatic life reached astonishing levels of diversity. The most notable evolutionary development was the rapid diversification of jawed fishes. Placoderms, heavily armored fishes equipped with powerful jaws, reached their peak during this time. The iconic Dunkleosteus, which could grow up to 10 meters in length, stood as a terrifying apex predator capable of crushing its prey with immense force. At the same time, cartilaginous fishes, the ancestors of modern sharks and rays, diversified, as did bony fishes. Among bony fishes, the Sarcopterygians, or lobe-finned fishes, including coelacanths and lungfishes, are of particular significance. Their fleshy, bone-supported fins represented a crucial pre-adaptation for life on land, setting the stage for one of the most important evolutionary transitions in Earth's history. Marine ecosystems thrived overall, with the emergence of ammonoids and the continued abundance of crinoids and coral reef systems. Yet the true revolution of the Devonian unfolded on land. During this period, terrestrial plants evolved from small, moisture-bound forms into organisms capable of colonizing vast areas, giving rise to the first true forests. Plants developed critical adaptations such as deep rooting systems, lignified stems that formed true wood for structural support, and broad leaves capable of efficient photosynthesis. The evolution of wood was a pivotal innovation, allowing plants to grow taller and form tree-like structures such as Archaeopteryx. These expansive forests dramatically altered the global carbon cycle, locking away enormous amounts of carbon and contributing to a gradual cooling of the planet. With forests established, the land became increasingly hospitable to animal life. Arthropods continued to diversify, with the appearance of the first wingless insects and a growing variety of arachnids thriving within forested environments. But the most profound step in terrestrial colonization came with the emergence of the first tetrapods. Still closely tied to aquatic habitats, animals such as Acanthostega and Ichthyostega represent a monumental evolutionary milestone. These fish with limbs possessed modified lobe fins that functioned as primitive legs, along with the development of a neck that allowed independent head movement. They ventured onto land for short periods, likely moving between shallow water bodies or navigating swampy environments. Their anatomy, blending features of both fishes and early amphibians, makes them key transitional fossils that mark the beginning of the evolutionary lineage leading to all terrestrial vertebrates. Toward the end of the Devonian, around 359 million years ago, Earth experienced a prolonged ecological crisis known as the Late Devonian Extinction, including the Kellwasser events. This extinction primarily affected marine life, particularly coral reef systems and placoderm fishes. It was likely driven by a combination of factors. One leading hypothesis links the extinction to climate change triggered by the expansion of terrestrial forests. By removing large amounts of carbon dioxide from the atmosphere, plants weakened the greenhouse effect, leading to global cooling. This cooling may have caused minor glaciations and significant fluctuations in sea level. In addition, the increased flow of organic matter into the oceans from plant-rich landscapes may have contributed to widespread oxygen depletion, creating anoxic conditions lethal to many marine organisms. The late Devonian extinction reshaped ecosystems worldwide, paving the way for new evolutionary innovations during the Carboniferous. The Devonian was therefore a period of profound transition. From a world dominated by water and fishes, Earth began to transform into a planet with vast green continents, where forests took root and the first vertebrates dared to set foot on land. It marked the opening of an entirely new chapter in the history of life, one that would forever change the trajectory of evolution on our planet. Following the late Devonian extinction, Earth entered the Carboniferous, a period spanning from approximately 359 to 299 million years ago. Its name, which literally means coal-bearing, reflects the formation of immense swampy tropical forests that gave rise to vast coal deposits. It was an era in which amphibians reached their peak, reptiles made their first appearance, and insects grew to colossal sizes, dramatically transforming terrestrial landscapes. Geologically, the Carboniferous was a time of intense tectonic activity and supercontinent formation. The collision between Euramerica and Gondwana began to assemble Pangaea, the ultimate supercontinent. This process triggered major mountain-building events, including the rise of the Appalachian Mountains in North America and the Variscan Ranges in Europe, creating vast and imposing chains. In the southern hemisphere, Gondwana's movement toward the South Pole led to extensive glaciation. The Carboniferous climate was variable. Early in the period, Conditions were warm and humid, ideal for the expansion of dense tropical forests. However, during the Pennsylvanian sub-period, Earth experienced significant global cooling that culminated in the Carboniferous Permian glaciation. Massive ice sheets formed across Gondwana. This cooling is largely attributed to the widespread proliferation of terrestrial plants, which removed enormous amounts of carbon dioxide from the atmosphere through photosynthesis, dramatically weakening the greenhouse effect. At the same time, the burial of organic matter as coal prevented carbon from returning to the atmosphere, further amplifying global cooling. Atmospheric oxygen levels reached their highest known concentrations, possibly around 35%, with profound consequences for terrestrial life, particularly arthropods. The defining feature of the Carboniferous was the expansion of coal forests. Vast tropical wetlands covered low-lying regions, dominated by tree-sized lycophytes such as lepidodendron, giant horsetails like calamites, tree ferns, and the earliest gymnosperms, seed-bearing plants including primitive conifers. The accumulation of this dense vegetation in oxygen-poor swamp environments led to the formation of the immense coal deposits we mine today. This enormous biomass profoundly altered the global carbon cycle, lowering atmospheric carbon dioxide and raising oxygen levels, a phenomenon often referred to as the Carboniferous effect. Animal life flourished alongside these changes. The Carboniferous marked the golden age of amphibians. Tetrapods diversified dramatically, colonizing swampy environments. Amphibians such as Ariops and Diplocaulus dominated aquatic and semi-aquatic habitats. Yet the most significant evolutionary innovation of the period was the emergence of reptiles. Descended from amphibian ancestors, reptiles were distinguished by the development of the amniotic egg. This egg, protected by a shell and internal membranes, freed reptiles from the need to return to water to reproduce, allowing them to colonize drier environments. Fossils such as Hylonomus provide clear evidence of their early presence. Terrestrial invertebrates also thrived and reached gigantic sizes, fueled by the unusually high oxygen levels. Insects underwent a massive evolutionary radiation. Giant dragonflies like Meganeura possessed wingspans of up to 75 centimeters, while enormous millipedes such as Arthropleura could exceed 2 meters in length. These arthropods formed the foundation of terrestrial food webs. The structural complexity of Carboniferous forests created a multitude of ecological niches, and the evolution of seeds in gymnosperms enabled plants to spread into drier habitats beyond swampy lowlands. In the oceans, cartilaginous fishes, including early sharks, diversified extensively. Bony fishes continued to evolve, while lungfishes and coelacanths persisted. Marine invertebrates such as crinoids, brachiopods, and ammonoids remained abundant, contributing to rich and productive marine ecosystems. The end of the Carboniferous was not marked by a sudden mass extinction, but rather by a gradual climatic shift driven by ongoing glaciation. Global cooling and increasingly dry conditions placed growing pressure on amphibian-dominated ecosystems. These changing conditions set the stage for the Permian period, during which reptiles, thanks to their amniotic eggs, would be better equipped to thrive in an increasingly arid world. The Carboniferous was therefore a time of profound transformation. It left an indelible mark on the geological record in the form of coal and gave rise to complex terrestrial ecosystems marked by the emergence of vast forests and the appearance of vertebrates truly independent of water. It was an era in which life flourished and reshaped Earth's biosphere forever. Following the Carboniferous, an age of vast forests and giant insects, Earth entered the Permian, a period that lasted from approximately 299 million to 252 million years ago. This interval marked the culmination of a single global supercontinent and witnessed the diversification of new forms of life, especially reptiles. Yet the Permian is most infamous for ending with the most catastrophic mass extinction in the history of our planet, a cataclysm that would radically alter the course of life on Earth. Geologically, the Permian was dominated by the final assembly of Pangaea. Continents that had been gradually converging during the Carboniferous, such as Gondwana and Euramerica, finally collided to form a single, colossal landmass that encompassed nearly all of Earth's continental surface. This continental fusion had profound geographic and climatic consequences. Orogenic collisions continued, raising vast mountain ranges within the interior of the supercontinent, including the Ural Mountains, formed by the collision between Europe and Siberia. The existence of Pangaea meant that a single immense ocean, Panthalassa, surrounded the landmass, while an inland sea, the Tethys Ocean, lay along its eastern margin. The formation of Pangaea dramatically altered oceanic and atmospheric circulation patterns, exerting a decisive influence on global climate. The Permian climate was notably more arid and seasonal than that of the Carboniferous, especially within the vast interior of Pangaea, far from the moderating influence of the oceans. Although the Carboniferous Permian glaciations persisted into the early Permian across southern Gondwana, global conditions gradually shifted toward increasing warmth and dryness as the period progressed. The creation of Pangaea produced an extreme continental climate effect. Winters were bitterly cold and summers intensely hot in the continental interior, with limited precipitation. The reduction in atmospheric carbon dioxide levels that had begun during the Carboniferous, driven by the expansion of forests and the burial of carbon as coal, continued into the early Permian, contributing to cooler and drier conditions in some regions. Later, this trend would be dramatically reversed by massive volcanism near the end of the Permian. Atmospheric oxygen levels also began to decline from their Carboniferous highs. Permian vegetation adapted to these changing climatic conditions. The extensive coal swamps of the Carboniferous diminished as climates became drier and cooler across many regions. Gymnosperms, seed-producing plants that had first appeared during the Devonian and Carboniferous, became the most successful and dominant plant group. Thanks to their ability to reproduce using seeds that contain a protected embryo and stored nutrients, and their independence from liquid water for fertilization through wind-transported pollen, gymnosperms were able to colonize much drier environments. Primitive conifers, ginkgos, and cycads began forming forests across uplands and arid regions. This diversification of drought-tolerant vegetation stands as a testament to evolutionary resilience in the face of environmental change. The rise and expansion of gymnosperms represented a direct evolutionary response to increasing continentality and aridity. Innovations such as protected seeds and wind pollination, which eliminated the need for free-standing water during reproduction, gave these plants a decisive competitive advantage over the ferns and lycophytes that had dominated Carboniferous swamps. This botanical shift not only transformed forest composition, but also altered resource availability for terrestrial herbivores, driving new evolutionary adaptations in animal life. In terms of terrestrial fauna, the Permian was the age of early reptiles and non-mammalian synapsids, often referred to as mammal-like reptiles. Reptiles, freed from dependence on water for reproduction by the amniotic egg, flourished and diversified rapidly. Well adapted to drier climates, they became dominant terrestrial vertebrates. Synapsids, including pelycosaurs such as the famous Dimetrodon, with its distinctive dorsal sail likely used for thermoregulation, and therapsids, the group that includes the ancestors of mammals, were particularly successful. Pelycosaurs included both predators and herbivores, while therapsids, which appeared later in the Permian, formed a highly diverse group displaying increasingly mammal-like traits, such as differentiated teeth, a more upright posture, and evidence of higher metabolic rates. These animals dominated Permian terrestrial ecosystems, occupying a wide range of ecological niches from apex predators to massive herbivores. Amphibians, though reduced in diversity compared to their Carboniferous peak, persisted in wetter environments such as swamps and floodplains, but were increasingly overshadowed by the expansion of reptiles across terrestrial ecosystems. Insects remained diverse, although the gigantic sizes seen during the Carboniferous declined as atmospheric oxygen levels fell toward more modern values. New insect groups appeared, and the coevolution between plants and their herbivores or early pollinators intensified. The reduction in arthropod gigantism correlates closely with declining oxygen concentrations, underscoring the intimate connection between atmospheric composition and biological form. In the oceans, marine life also underwent renewal and diversification. Bony fishes continued their rise, while sharks and other cartilaginous fishes became more abundant and increasingly modern in appearance. However, many of the dominant Paleozoic marine groups, such as trilobites, which had been ubiquitous since the Cambrian, were in decline, reduced to a handful of species before their final disappearance. Ammonoids continued to thrive, and brachiopods and crinoids remained important components of benthic ecosystems. Marine reefs persisted as well, though with compositions distinct from earlier eras, reflecting a gradual restructuring of marine biodiversity. The culmination of the Permian, however, marks the darkest chapter in its history: the Permian Triassic mass extinction, known as the Great Dying. This cataclysm, which occurred around 252 million years ago, was the most devastating extinction event in the history of life on Earth. It is estimated that approximately 96% of all marine species and 70% of terrestrial vertebrate species vanished over a geologically brief interval, perhaps tens to hundreds of thousands of years. Entire groups of organisms, including trilobites, placoderms, and many brachiopods, disappeared forever, bringing the Paleozoic era to an abrupt end. This event defines the boundary between the Paleozoic and Mesozoic eras. The primary cause of this extinction is attributed to unprecedented large-scale volcanism in what is now known as the Siberian Traps, a vast igneous province in present-day Russia. Over an extended period, enormous volcanic eruptions released colossal quantities of carbon dioxide, sulfur dioxide, and other volatile gases into the atmosphere. This triggered rapid and extreme global warming, with temperature increases of up to 10 degrees Celsius, leading to widespread oceanic anoxia, a severe depletion of oxygen in the seas. Warming reduced the solubility of oxygen in seawater and slowed ocean circulation, creating vast dead zones devoid of life. At the same time, ocean acidification, caused by the absorption of atmospheric carbon dioxide, devastated organisms with calcium carbonate shells and skeletons. On land, the consequences were equally catastrophic. The release of methane from oceanic clathrates, an even more potent greenhouse gas, further amplified warming and widespread drought. Sulfur emissions likely produced acid rain, damaging vegetation and acidifying soils. Food webs, both marine and terrestrial, collapsed entirely. The destruction of forests and the loss of dominant herbivores and predators created a post-apocalyptic world, a desolate planet in which life was forced to begin anew. The Great Dying was a profound biological reset, eliminating the majority of Paleozoic life forms and clearing the way for the radiation of new species during the Mesozoic era that followed, the Age of Dinosaurs. Recovery from this catastrophe took millions of years, a testament to its sheer magnitude. Estimates suggest that it required between 5 and 10 million years for biodiversity to rebound and for complex ecosystems to re-establish themselves, marking the dawn of a new geological and biological era. After the great dying of the Permian, which left Earth devastated and on the brink of biological collapse, our planet entered the Triassic. This period, spanning from approximately 252 million to 201 million years ago, marks the first chapter of the Mesozoic era, often called the Age of Reptiles. It was a time of slow but steady biological recovery, the emergence of new groups of plants and animals, and, most importantly, the dawn of the dinosaurs, which would go on to dominate terrestrial ecosystems for the next 135 million years. Geologically, the Triassic was defined by the presence of the supercontinent Pangaea, which had fully assembled by the end of the Permian. Pangaea was an immense landmass stretching from pole to pole, bordered by the vast Panthalassa Ocean. Within its eastern margin, the Tethys Sea was beginning to open as a broad embayment. The sheer size of Pangaea meant that much of the continental crust stood well above sea level, and the intense mountain building that had characterized the Carboniferous and Permian waned, giving way to a more extensional tectonic regime. Toward the end of the Triassic, however, the first signs of Pangaea's fragmentation appeared, with the formation of rift systems and sedimentary basins that would eventually split the supercontinent apart. The existence of Pangaea profoundly influenced global climate and ocean circulation in ways never seen before. The Triassic climate was strongly shaped by the presence of this supercontinent. Global temperatures were generally warm, and there is no evidence for permanent polar ice caps. The immense interior of Pangaea experienced extreme continental conditions, with scorching summers and very cold winters, far removed from the moderating influence of the oceans. Coastal regions, by contrast, were subject to monsoonal climates, with strong seasonal rainfall. Atmospheric carbon dioxide levels remained high, a legacy of the intense volcanic activity associated with the Siberian traps that had driven the Permian extinction. This contributed to a strong greenhouse effect and elevated global temperatures. Oxygen levels, which had dropped sharply during the Permian crisis, recovered only slowly throughout the Triassic. Triassic terrestrial vegetation reflected these drier climatic conditions. Gymnosperms, which had already risen to prominence during the Permian, continued to diversify and dominate. Forests were composed mainly of conifers, cycads, palm-like plants with large cones, ginkgos, and seed ferns. These drought-tolerant plants formed the backbone of terrestrial ecosystems. The vast coal swamps of the Carboniferous were long gone, but vegetation continued to spread across the continents, stabilizing soils and supporting emerging terrestrial food webs. The resilience and adaptability of these plant communities in a post-extinction world is remarkable. In terms of terrestrial animal life, the Triassic was a period of recovery and expansion. The few non-mammalian synapsids, often called mammal-like reptiles, that survived the Great Dying were initially the dominant land animals. Decinodonts, herbivores with beaked, toothless jaws, recovered rapidly and became extremely abundant during the early and middle Triassic. One notable example is Lystrosaurus, whose widespread distribution across the globe in the early Triassic provides some of the strongest evidence for the existence of Pangaea. Cynodonts, another group of synapsids, continued to evolve and displayed increasingly mammalian traits, including more advanced tooth differentiation and possible signs of warm-bloodedness. From this lineage, the first true mammals would emerge toward the end of the Triassic, though they remained small, inconspicuous creatures living in the shadows of the dominant reptiles. The true rising stars of the Triassic, however, were the archosaurs. This group of reptiles, which includes the ancestors of dinosaurs, pterosaurs, and crocodiles, began its ascent during the Middle Triassic. Crurotarsans, the lineage that would eventually give rise to modern crocodilians, diversified into a wide array of terrestrial, semi-aquatic, and fully aquatic forms. Many of them were apex predators long before dinosaurs rose to dominance. It was during the middle to early late Triassic, around 230 million years ago, that dinosaurs made their first appearance. The earliest dinosaurs, such as Eoraptor and Herrerasaurus, were small to medium-sized bipedal animals, no larger than a dog or a small pony. They originated in what is now South America and lived alongside synapsids and crurotarsans. At first, they were not the dominant animals in their environments, yet their anatomical adaptations, including an upright posture, potentially higher metabolic rates, and greater locomotor efficiency, gave them subtle but important competitive advantages that would become decisive in later periods. It is striking to consider that these future giants began in such a humble and unassuming way. Terrestrial invertebrates also continued to thrive. Insects diversified further, including the expansion of flying insects such as beetles and flies, as well as the appearance of the first insects with complete metamorphosis, the holometabolans, whose life cycles included distinct larval, pupal, and adult stages. In the oceans, life also recovered from the Permian extinction, though along new evolutionary pathways. Marine reefs began to re-establish themselves, though with a different coral composition than in the Paleozoic. Ammonoids experienced a remarkable recovery and became extremely important index fossils for dating Triassic rocks. Both bony and cartilaginous fishes continued to diversify, including early sharks with increasingly modern body plans. New groups of marine reptiles emerged and flourished, including ichthyosaurs, dolphin or shark-shaped predators with highly streamlined bodies, plesiosaurs with broad bodies and long necks, and nothosaurs, elongated marine reptiles with webbed limbs that occupied predatory niches in shallow seas. Although descended from terrestrial ancestors, these marine reptiles became fully adapted to life in water, displaying striking examples of convergent evolution with fishes and later marine mammals. The end of the Triassic, around 201 million years ago, was once again marked by a mass extinction event, though less severe than the Permian catastrophe. Known as the Triassic-Jurassic extinction, this event eliminated many large amphibians, most non-crocodilian crurotarsans, and a significant number of marine invertebrates. The extinction is commonly linked to intense volcanic activity associated with the initial breakup of Pangaea and the formation of the Central Atlantic Magmatic Province. Massive eruptions released enormous quantities of gases into the atmosphere, triggering global warming and possibly ocean acidification. This extinction had a decisive evolutionary consequence. By removing most of the dinosaurs' major competitors, it cleared the ecological stage for their rise to dominance. While many large non-dinosaurian archosaurs vanished, dinosaurs somehow survived and rapidly diversified in the late Triassic and early Jurassic. The Triassic, therefore, was not only a period of recovery and new beginnings, but also the setting of an evolutionary turning point, a biological game of thrones in which the foundations of the age of dinosaurs were laid within a constantly changing world. It was a fundamental transition, a time when life reorganized itself and prepared for its next great chapter in evolution. After the Triassic-Jurassic extinction, an event that effectively reset the evolutionary stage, Earth entered the Jurassic, a period spanning from about 201 million to 145 million years ago. This was, without question, the time when dinosaurs not only consolidated their dominance, but reached colossal sizes and astonishing diversity, becoming the undisputed rulers of the continents. Life on land, in the oceans, and in the skies experienced a remarkable expansion of new forms, marking an era of abundance and spectacle. Geologically, the Jurassic was defined by the continued breakup of Pangaea. This immense supercontinent began to split into two major land masses: Laurasia in the north, comprising what is now North America and Eurasia, and Gondwana in the south. The opening of the Central Atlantic Ocean initiated the separation of Africa and South America from North America. These extensional tectonic movements not only created new ocean basins, but also generated intense volcanic activity along newly forming mid-ocean ridges. Continental margins were flooded by vast epicontinental seas, such as the Sundance Sea in North America, which were rich in marine life and became major sites of sediment accumulation. This continental reorganization profoundly altered oceanic and atmospheric circulation patterns, reshaping the global climate. The Jurassic climate was predominantly warm and humid worldwide, with no evidence of polar glaciations. Atmospheric carbon dioxide levels were high, sustaining a strong greenhouse effect that kept temperatures mild even at high latitudes. The fragmentation of Pangaea and the formation of new inland seas increased global humidity, leading to more abundant rainfall than during the arid Triassic. These warm, moist conditions were ideal for the flourishing of lush vegetation across much of the planet. Jurassic terrestrial vegetation was rich and dominated by gymnosperms. Vast forests of conifers covered the landscapes, including araucarians, early pines and fir-like trees, cycads with short trunks and palm-like fronds, and ginkgos with their distinctive fan-shaped leaves. Ferns and horsetails were also widespread, particularly in wetter environments. These extensive forests provided an enormous food supply for herbivorous dinosaurs, which in turn supported complex terrestrial food webs. The emergence of more efficient gymnosperm groups further fueled the expansion of forest ecosystems. In terms of terrestrial animal life, the Jurassic was truly the age of dinosaurs. Dinosaurs diversified into an extraordinary array of forms and sizes, from small, agile bipedal hunters to the largest land animals ever to walk the earth. Sauropods, such as the iconic Brachiosaurus, Diplodocus, and Apatosaurus, reached truly colossal proportions, with some exceeding 30 meters in length and weighing tens of tons. These long-necked herbivores fed on the abundant tree-level vegetation, and many likely relied on group behavior or sheer size as protection against predators. Carnivorous theropods also thrived. Allosaurus, an apex predator of the late Jurassic, used its powerful jaws and sharp claws to hunt large sauropods and other herbivores. Other notable dinosaur groups included stegosaurs, recognized by their distinctive dorsal plates and spiked tails, and early ornithopods, herbivorous dinosaurs that would diversify even further during the Cretaceous. Dinosaurs filled an immense range of ecological niches, dominating virtually every terrestrial environment. Alongside the dinosaurs, mammals persisted, though they remained small, mostly nocturnal, and ecologically marginal, living in the shadows of the giant reptiles. Even so, they diversified in form and began developing more specialized traits. Lizards and turtles also appeared and diversified during this time. insects continued their evolutionary expansion, with new groups emerging, including early butterflies and moths. The Jurassic also marked a major chapter in the conquest of the skies by reptiles. Pterosaurs, flying reptiles closely related to dinosaurs, though not dinosaurs themselves, reached impressive levels of size and diversity. Ranging from small pterodactyl-like forms to much larger species, they dominated aerial ecosystems. Their wings consisted of a membrane of skin and muscle, supported primarily by a single elongated finger. At the same time, one of the most significant evolutionary milestones of the period occurred with the appearance of the first birds. Archaeopteryx, famous for its combination of feathers, teeth, and clawed wings, represents a remarkable blend of reptilian and avian features and marks the beginning of avian evolution during the late Jurassic. In the oceans, marine life continued to recover and diversify. Ichthyosaurs and plesiosaurs, including both long-necked and short-necked forms, dominated the seas as marine predators. Marine crocodilians, such as thalattosuchians, were also common. Ammonoids reached peak diversity and complexity, serving as key index fossils for dating Jurassic rocks, while belemnites, relatives of modern squids, were extremely abundant. Modern bony fishes underwent a significant radiation, and sharks continued to evolve toward more advanced forms. Coral reefs remained important marine ecosystems, though their species composition differed from those of the Paleozoic. In essence, the Jurassic was the golden age of giant reptiles, a time of extraordinary biological richness and dramatically transformed landscapes. The land, seas, and skies were filled with remarkable creatures, setting the stage for the final act of dinosaur dominance that would unfold in the Cretaceous. Following the splendor of the Jurassic, the Cretaceous, from the Latin creta, meaning chalk, spanned from approximately 145 million to 66 million years ago. It was the final and longest period of the Mesozoic era, a time that witnessed the diversification of flowering plants, the last great flourishing of the dinosaurs, and their sudden and dramatic end, an event that would redefine life on Earth forever. Geologically, the Cretaceous was marked by the continued and accelerated fragmentation of Pangaea. Laurasia and Gondwana drifted farther apart, and the continents began to assume shapes more recognizable to us today. The Atlantic Ocean widened significantly, separating South America from Africa and North America from Eurasia. India broke away from Madagascar and began its rapid northward journey toward its eventual collision with Asia. The Cretaceous also saw the formation of vast epicontinental seas that flooded large portions of the continents, such as the Western Interior Seaway, which split North America into two land masses. The intense tectonic activity along mid-ocean ridges driving this continental separation also contributed to increased rates of submarine volcanism. Sea levels during the Cretaceous were the highest of the entire Phanerozoic eon. The expansion and warming of oceanic ridges caused the seafloor to rise, leading to a global increase in sea level and the inundation of extensive low-lying regions. These shallow marine environments became ideal habitats for marine life and, upon the death of countless microorganisms, led to the accumulation of massive chalk deposits that give the period its name. The Cretaceous climate was predominantly warm and remarkably uniform across the globe, even more so than during the Jurassic. Global temperatures were significantly higher than those of today, and there were no permanent polar ice caps, sustained by a powerful greenhouse effect. The absence of polar ice and the overall warmth meant that tropical and subtropical ecosystems extended much closer to the poles than they do in the modern world. Terrestrial vegetation underwent a profound transformation during the Cretaceous, with the rise of angiosperms, or flowering plants. Although they first appeared in the early Cretaceous, angiosperms experienced an extraordinary diversification and rapidly became the dominant plant group in most terrestrial ecosystems. Their success was driven by several key innovations: flowers that attracted pollinators, primarily insects, enabling more efficient and specialized reproduction; seeds enclosed within fruits, which protected them and aided in their dispersal; and faster growth and reproductive cycles. This close coevolution with insect pollinators fueled the diversification of both plants and insects. By the late Cretaceous, landscapes filled with broad-leafed trees and flowering plants would have begun to resemble modern environments. Even so, conifers, cycads, and ferns remained important components of the flora. In terms of terrestrial animal life, the Cretaceous represented the final zenith of the dinosaurs. They reached their greatest diversity and specialization, producing many of the iconic forms that dominate popular imagination today. Tyrannosaurids, such as the formidable Tyrannosaurus rex, became apex predators, armed with bone-crushing jaws. Triceratopsians, massive herbivores with bony frills and 3 horns, grazed in herds. Hadrosaurs, or duck-billed dinosaurs like Maiasaura, evolved complex dental batteries capable of processing the tougher, more fibrous vegetation produced by flowering plants. Ankylosaurs, heavily armored dinosaurs with tail clubs, possessed near impenetrable defenses. Meanwhile, smaller, agile predators, such as velociraptors, showcased the speed, agility, and intelligence of certain theropods. The interactions between herbivorous and carnivorous dinosaurs created complex and dynamic terrestrial ecosystems. At the same time, mammals continued to evolve quietly beneath the shadow of the dinosaurs. Though still small and mostly nocturnal, they diversified into a variety of forms and ecological roles, including insectivores and small herbivores. The first marsupials and placental mammals, the 2 major groups of modern mammals, appeared during the Cretaceous, laying the groundwork for their dramatic adaptive radiation in the Cenozoic era. In the skies, pterosaurs maintained their dominance as the primary flying vertebrates, evolving increasingly specialized forms, with some, such as Quetzalcoatlus, achieving the largest wingspans ever known among flying animals. However, birds, which had first appeared during the Jurassic, expanded significantly during the Cretaceous. They diversified into a wide range of forms and began occupying an increasing number of ecological niches, setting the stage for their explosive diversification after the extinction of pterosaurs and non-avian dinosaurs. In the oceans, plesiosaurs and ichthyosaurs continued to dominate marine ecosystems, although ichthyosaurs declined toward the end of the period. Mosasaurs, large predatory marine reptiles, emerged during the late Cretaceous and became the supreme predators of the seas, rivaling sharks in both size and ferocity. The proliferation of calcareous plankton in the oceans led to the formation of vast chalk deposits and supported the diversification of many marine organisms that fed upon them, including numerous fishes and marine reptiles. Tragically, the majestic reign of the dinosaurs came to an abrupt and catastrophic end around 66 million years ago. The Cretaceous-Paleogene extinction event, commonly known as the KPG extinction and formerly called the Cretaceous Tertiary extinction, delivered the final blow to the non-avian dinosaurs and countless other forms of life. This event marks the boundary between the Mesozoic era and the Cenozoic era. It was one of the 5 great mass extinctions in Earth's history, and although it was not the largest in terms of the percentage of species lost, it is the most famous due to the prominence of its victims. the most compelling and widely accepted evidence for the cause of this extinction points to the impact of a giant asteroid. The definitive smoking gun is the Chicxulub crater, an impact structure approximately 180 kilometers in diameter, buried beneath the Yucatan Peninsula in Mexico. The evidence supporting this hypothesis is overwhelming. In the 1980s, scientists Luis and Walter Alvarez discovered a thin layer of clay enriched with iridium in sediments at the KPG boundary all over the world. Iridium is rare in Earth's crust, but abundant in asteroids and comets. The later identification of the Chicxulub crater, precisely dated to the time of the extinction, sealed the case. In addition to iridium, KPG boundary sediments contain shocked quartz, microspherules formed from molten rock that solidified in the air after the impact, and soot, clear evidence of massive global wildfires. The impact of an asteroid roughly 12 kilometers in diameter released an amount of energy equivalent to billions of atomic bombs. The immediate effects were devastating. The impact into the ocean generated colossal mega-tsunamis that ravaged coastlines thousands of kilometers away. A powerful shockwave propagated through the atmosphere, followed by an intense heat pulse that ignited vast areas of vegetation, triggering global wildfires that injected enormous quantities of soot into the atmosphere. This immense cloud of dust, ash, and aerosols blocked sunlight for months or even years, causing a global impact winter. Temperatures dropped sharply, photosynthesis was largely shut down, and plants began to die. At the same time, the vaporization of sulfur-rich rocks at the impact site, along with the release of additional gases, produced widespread acid rain, acidifying both oceans and soils. The consequences of this catastrophe were disastrous for life on Earth. The collapse of photosynthesis caused food chains to unravel, first in the oceans with the loss of plankton, and then on land. Herbivores starved, followed by carnivores. A wave of extinction swept across the planet. All non-avian dinosaurs vanished, leaving only birds as their living descendants. Pterosaurs disappeared entirely, as did most mosasaurs and plesiosaurs. Many groups of marine ammonoids and belemnites went extinct, along with a large proportion of oceanic plankton. It is estimated that the Cretaceous-Paleogene extinction eliminated roughly 75% of all species on Earth. Yet the question remains: who survived and why? Organisms capable of enduring darkness, cold, food scarcity, and extreme environmental instability had the greatest chances of survival. Small mammals, often nocturnal and feeding on insects, seeds, or detritus, managed to pass through this evolutionary bottleneck. Birds, the only surviving dinosaurs, along with crocodiles, turtles, lizards, many amphibians, and numerous fish species also endured. Their lower energy requirements, ability to hibernate, burrow, or live in aquatic refuges may have been crucial advantages. Once again, life demonstrated its extraordinary resilience, though at an unimaginable cost. This extinction event marked the end of the Mesozoic era and the beginning of the Cenozoic era, often called the Age of Mammals. With the disappearance of the dinosaurs, vast ecological niches were suddenly left vacant, setting the stage for the adaptive radiation of mammals and birds, which would rapidly diversify and come to dominate terrestrial ecosystems in the New World. The Chicxulub impact did not merely end an era. It reshaped the trajectory of life on Earth and ultimately paved the way for the emergence of our own species. If you enjoyed this video, don't forget to subscribe to the channel so we can continue exploring the mysteries of the past together. See you in the next Jurassic adventure.